Phenols. Phenols are a very important class of compounds which has versatile application in many of the fields of organic chemistry. First, we shall pass on the methods of preparation, and our first discussion will be from benzene. Phenol can be prepared from benzene in two discrete ways. One is through diazonium, one is without diazonium. We will be discussing both of them. If it is without diazonium, then what we do? We add concentrate sulfuric acid to benzene. And as soon as we add concentrate sulfuric acid, it forms SO3H. That is benzene sulfonic acid. As it is an acid, it is reacted with dilute NaOH. An acid-base reaction takes place. It forms SO3Na. In this salt, SO3Na, we treat with NaOH solid, heat it rather, with NaOH solid pellets, whereby SO2 is eliminated, forming ONA, known as sodium phenate. And after formation of sodium phenate, we simply hydrolyze this with water to form the phenol. Step 2, via diazonium. Benzene is there. To undergo diazonium, we need aniline, and for aniline, we need nitrobenzene. So in the first step, we form nitrobenzene. After formation of nitrobenzene, we reduce it with tin-HCl to form aniline. After reduction with aniline, we undergo the diazonium coupling reaction, NO2HCl, low temperature followed by addition of water with slight amount of heat. The compound will be converted to phenol. So these are the two direct ways by which we can prepare phenol from benzene. One is with diazonium, the other is without diazonium. Now, apart from that, phenol can also be prepared from halobenzenes. If I have to prepare phenol from halobenzene, it is very clear to convert one functional group to the other, I need to undergo a substitution reaction. But as I have told you earlier, in chlorobenzenes, direct substitution is not possible because the carbon-chlorine bond has partial double bond character. So what we need to do? We need to attach NO2 group at the para position by simply nitration. So we need to add concentrate sulfuric acid and nitric acid for nitration. So this will become Cl along with NO2. Now we want to remove the Cl, so we heat with OH minus. Immediately after heating with OH minus, this will be converted to your phenol, but still there will be a NO2 group left over. Now this NO2 we have introduced for your own safety, own advantage. Now you have to throw it. How to remove the NO2 group? Simple. First convert this to NH2 by reduction, then convert this to diazo, and then simply treat with H3PO2. As I have told you in the reaction, while treating diazo, this H3PO2 will undergo a free radical mechanism and this NO2 will go off. So there is a conversion. After discussing from halobenzene, the fourth method of conversion, which is also used, is from Cumene hydroperoxide. This we have discussed under the chapter of rearrangement. If you recollect it, or if you look into the chapter, this was cumene. Cumene is nothing but isopropyl benzene. When this is first treated with oxygen, under pressure, this was converted to a compound called cumene hydroperoxide, COOH, with the two methyls present as usual. This is the starting material called cumene hydroperoxide. After this compound was treated with H+. So as soon as the compound was treated with H+, there was a protonation over here, and this group leaves. As soon as the group leaves, there is a positive charge coming on this oxygen, which is detrimental because oxygen being an electronegative element will never tolerate any such positive charge. So then what happens, from the adjacent carbon, out of the three groups, methyl, and phenyl, the one with maximum electron density migrates. And as all of us know, phenyl has the maximum density, therefore the phenyl migrates, resulting in the formation of CH3. CH3, this was already there, plus will be there on carbon, and this will become OPH. After this, the water molecule in the medium will attack over here, and therefore the positive charge will go away, and we'll have OH over here. And after the formation of OH, this will tautomerize back, and this part will go out. So this part will become acetone as a byproduct, and this part will be your phenol. So by cumene hydroperoxide mechanism, we'll always get phenol because phenyl has a stronger or higher migratory aptitude because of its more electron density as compared to the methyls. So methyl will never migrate in this kind of rearrangement. The last one of the rearrangement comes under the heading of allylic rearrangement, which also we have discussed during rearrangement part. O CH2, CH double bond CH2. Pleasant rearrangement or allylic rearrangement. In this what happens, these are pi bonds over present. This pi bond attacks here, this goes here, this comes over here. So eventually we have C double bond O, CH2, this C, if I call it as gamma, so this is the gamma 1. CH double bond CH2 with the H hanging from here. In the next step, this H which was there will go back. The pi bonds, other pi bonds are as usual. This will aromatize. So from this we'll also get phenol, and the other part of the chain as usual, CH2, the gamma carbon, CH double bond CH. So these are some of the important methods by which we prepare phenol. Next we shall go into the properties or tests for phenol. Whenever there is a functional group, phenolic functional group, that can be identified very readily by reaction with Fe3+, that is ferric chloride. Whenever we have a phenol, if phenol in alkaline medium is treated with ferric chloride solution, that is Fe3+, a violet color is developed. The production of the violet color in the test tube indicates beyond doubt that the compound has a phenolic group. Now, how do we look at the mechanism? In an alkaline medium, we all know phenol is converted to phenoxide ion. So it becomes a ligand. And ferric ions are metals. So a metal will coordinate with a ligand OPH whole 6 because the coordination of iron is 6. Iron had a charge of +3. This had a charge of -1. So 6 will make it -6. So -3 will be left over. And this gives you a violet color. So the appearance of the violet color indicates the presence of phenolic group.